Okay, so in this video we're going to discuss kind of the concept behind integration, behind finding the area under curves. We've sort of went a little bit ahead and talked about the fundamental theorem of calculus, how we're going to actually compute integrals using antiderivatives. This is something we probably should have done first, which is what's really going on with an integral. And we're going to be referring to this when the next video up is going to be volumes of revolution. And so this is kind of laying the foundation for the concept of volumes of revolution, which is one of the trickier things in a first-year calculus course. So here we're gonna go absolutely from the basics. What are we doing with integration? If I have this function y is equal to f of x up here, and I want to find what I'm going to call the integral of f of x from, I'll do the same because I have my bounds here in this mauve color. This is going to be from a to b. Let me make this a little bit bigger. The integral from a to b of f of x, and I think I'll choose red for this, and you'll see why in a minute, f of x dx. And so this symbol that I just drew here, integral from a to b of f of x dx, this represents the area under this curve, the exact area under this curve here. And we're going to come up with a way to find this, and we're going to come up with a way to find it using limits. And this is the sort of theme of calculus, is that we can use limits to do things that we can't really do, and that kind of sounds strange. When we're finding derivatives, we don't actually, a derivative is an instantaneous rate of change. We don't have a way to find an instantaneous rate of change. We don't really know what it is actually, but we do know how to find average rates of change. And so what we do is we find smaller and smaller average rates of change around a point, and then we take the limit as the interval around the point gets smaller and smaller, and that gives us the instantaneous rate of change. If the limit exists, we say the function is differentiable and gives us the instantaneous rate of change. So we use those little triangles that we make, the slopes of those secant lines, the things that we know how to find, to take a limit, and that limit gives us the thing that we don't know how to find, which is the instantaneous rate of change. With integrals, we're going to do the same thing, except instead of little secant lines, slopes of secant lines, average rates of change, what we're going to be doing is taking something which we know how to find the area of, rectangles, and basically filling up the area underneath the graph of f in between these points with rectangles. And whenever we have a bunch of rectangles, we can find their area, and we're going to fill it up with more and more rectangles. Actually, from above and below, we're going to kind of squeeze it in between a bunch of rectangles. And if the limits of what we're going to call the lower sums and upper sums, if they're the same, then the actual area is going to get squeezed in between them. And so that's the idea. So without further ado, let's actually get to it. So how are we going to do this? Integration always starts with something called a partition of the interval, which we'll call P. And P is a set of points, x0, x1, all the way through xn, which basically chop up the interval. The x0 is always equal to a, and the xn is always equal to b, and then I put in the x1, x2, the 2, not the x, x2, all the way through. This is going to be, I'll just put in the ticks because I'm actually going to make it. But this kind of, there's no particular number assigned to the n, so this is going to be xn minus 1, and then the b is the xn, the a is the x0. And this chops up our interval, and that's the first thing we do. What's the second thing we do? Well, we're going to come up with what we call lower and upper sums. What's a lower sum? I'll actually draw it in first, and then write the formula for it. The lower sum, I'm going to start with the first interval from x0 to x1, and I'm going to, if I can stop this thing from turning into an eraser every 5 seconds, still grappling with that, sorry about this, I'm going to find the minimum value of the function on that interval. So on the interval from x0 to x1, the minimum value looks to be here, and I'm going to make this the side of the first rectangle, and this is going to be the top, and here we go. I have my first rectangle in the lower sum. Then I'm going to do the same thing. I'm going to go to x2, find the minimum value of the function on that interval, which looks to be about here. Roughly, I'm being sort of inexact with this, of course. The next one, this is going to be the same minimum value, so I connect it to about there, and then come down like that. The next one is going to be here. Sorry, I'm almost done with this. I promise to rotate this line up. Is it not straightening for me? Sorry. There we go. Like that. Okay. And finally, the last rectangle in our lower sum is going to be, so I have to pause to let these lines straighten themselves so it doesn't look completely disgusting. There we go. That's the last one. And so this is a lower sum with respect to this partition P, as we say. So I get my first, what we're going to call, I'll do it up here, my lower sum L, F, P, and this notation, of course, is encoding the fact that it's a lower sum, the function is f, and the partition is p. And this, I'm going to write this as, this is equal to the sum from k is equal to 0 to n of, I'm going to call this little m I, which is going to stand for the minimum value of the function on a particular interval. And then I'm going to multiply it by xi minus xi minus 1, which is the length of the ith subinterval in the partition. And that's this thing, that's this blue thing that we get here. Now, if I make this a uniform partition, so the way that I do this is I take A, and then I add b minus a over n to it, and I keep going like this. I should put in the second one here. So a plus b minus a over n plus 2 times b minus a over n, so adding another one, and all the way down to, last one is a plus n times b minus a over n. Well, the n's are actually going to cancel. As you can see, the n's here are going to cancel, and I get a plus b minus a, so it's actually just a. This a was secretly a plus 0 times b minus a over n. So I have this uniform partition. Each of the subintervals, xi minus 1, is actually, this part is just b minus a over n, and we can write this as delta x. So let's just keep in mind here that delta x is going to be b minus a over n. There's actually tons of ways to partition and take sums, but we're going to be, and it doesn't really matter which way you do it, it turns out, but we don't really care about this for now. We're just going to talk about uniform partitions because they're the easiest ones to work with. So I end up with my lower sum being the sum from k is equal to 0 to n of m of I delta x. The next thing I'm going to do is come up with what I call an upper sum, and let's use, what should we use for that? Maybe dark blue probably is no good. Let's just do the mauve, this kind of magenta thingy. Maybe purple, I think purple looks a little bit better. So this is going to be the exact same thing, except now I'm taking, that's a very thin line, I'm taking on each subinterval the maximum value of the function, and using that, my thing has gone away again, I'm sorry, it doesn't like me, keeps trying to run away, doesn't want to talk about integrals today. There we go, and connect them here. Great, and the next one is going to be like this. Again, taking the maximum value of the function on that subinterval. This one will be here, and I connect like that. Next one, this interval is not so illustrative because it's almost flat, but you kind of see what I get. And then the last one is going to be here. Just connect them like that, and then I get this. Okay, and this is my upper sum. And the upper sum I'm going to write as, I'll do it over here and you'll see why in a second, not L, but rather I'm going to write this as, and he's gone again, come back, the upper sum of f with respect to p, and this is, actually I'll do this, I'll push it even farther over to the right here, this is u f p, and this I write as the sum from n, k is equal to 0, now capital Mi times delta x. And capital Mi, in purple, it represents the largest value of f on any particular subinterval. And so there's two keys to this. The first one is that we can see that the actual area under the curve, which we denoted by this thing, this a to b, integral from a to b, f of x dx, this is always in between any lower sum or upper sum. it is always sandwiched in between. So this is integral from a to b, f of x dx. It's bigger than or equal to any lower sum, and it's less than or equal to any upper sum. And so that's the first observation we have. That lets us do this. The second observation is that if I do what's called refining the partition, so if I add points to the partition, so I cut all the intervals in half and throw in a bunch more points, well, what effect is this going to have on the lower sums and the upper sums? So I'll just do this one because it's going to sort of show us what's going on. I'll cut the thing here, and let's just do this in kind of like dots here, this blue. What's going to happen to the lower and upper sums? Well, the lower sum, actually I don't want those dots. You'll see what's going on with this. Let's do those in yellow. Maybe that's the color that we haven't used before. So I've chopped this thing in half. I've kind of cut, and I'm going to do this to each one of them, not just this one. I'm only doing one to illustrate it. But what's this going to do? Well, on the first bit, on the left part of this, the minimum value stays the same. It is absolutely the same, so I get, and I'm going to try to make these lines a little bit wider. I don't know why it's tapering. I can't get it to stop that, sorry. The minimum value is still going to be this right here, so the lower sum rectangle is going to be this guy right here. Let's maybe make him a bit brighter so we can see this more clearly. He's like that. Okay. But on the second interval, the right one here, the minimum point is now this. That is the new minimum on this interval. So my lower sum rectangle here actually becomes this guy. And so we can see that this thing here was added to it. This amount got added to the lower sum. So it got bigger, basically. The lower sum is going to increase. It actually could stay the same depending on how you pick them, but it's always going to get bigger, either stay the same or increase. What's happening to the upper sums? Well, again, so on this right side here, the maximum is still this point. So I still have this as the top of my, this is gross again, sorry, there we go. I still have this as the top of my upper sum, and this is going to be the side thing here. I have that's great. But now on the second interval, I've chopped it up here, so on the left interval there, the new subinterval, that is the highest portion, or the highest point. And so this portion here, this guy right there, that got subtracted from the upper sum. So what's happening as we refine the partition, and so with these uniform partitions, refining the partition would just mean increasing the n. Well, the lower sums are either staying the same or getting bigger, and the upper sums are either staying the same or getting smaller. And the whole time, no matter how I do this, the whole time, this guy is stuck in between them. And so just like when we found derivatives, we looked at the limit as h goes to 0 of f of a plus h minus f of a over h. If that existed, then we said that was the derivative at the point. Well, here we're going to be saying, maybe let me do this in orange again. I'm going to say that if, and I again don't know why he's switching back to an eraser on me. I swear, I mean, you can't see it, but trust me, I'm not touching the screen when that happens. I really have no idea what's going on. If the limit as n goes to infinity, I'll go back here, as n goes to infinity of the upper sum of f with respect to p, the upper sums of f with respect to p, so the p's are changing as n goes to infinity. We'll just call p is the uniform partition with n pieces in it. So u f of p minus l f p, if this is equal to 0, well, that means that they're going to the same limit. That means the limits are the same. The limit as that implies that the limit as n goes to infinity of u f p is equal to the limit as n goes to infinity of l f p. And by the squeeze theorem, what is in between them is actually the exact area, the integral from a to b of f of x dx. That is this thing. And so this is really cool. We actually were able to find this thing. We had no idea what it was, but we know what it was stuck in between. And so if we showed that it was getting squeezed in between two things, which are getting closer and closer together, there's no limit to how close together they can get. That's what this is saying. Then we know that common limit has to be the exact area under the curve. And so that's actually what is going on with integrals. They actually are integrals, limits of Riemann sums. But what I want to do, because it's a useful way to think of it, and again, now we're going to get really hand-wavy. Up until this point, we've been actually pretty formal about this, but I'm going to get now really hand-wavy, and tell you that you can, and I find that this really helps students, you can absolutely think about these integrals from a to b f of x dx as an infinite sum of infinitely thin sticks. And I think I touched on this in the fundamental theorem videos, and I'm going to touch on this again in the volumes of revolution videos. But I can think of this as at any point here, I have, and this is why I did it in red at the beginning of the video, that's why I did the dx in red. I'm going to think of this as this kind of line segment which has height f of x and infinitesimal width dx. So if I bring it over here, what's it going to look like? It's going to be this kind of thing. And sorry, just bear with me 1 second while I make these lines straight, because I think it's kind of worth it to not have them be totally gross. I'm looking at this kind of red line going from A to B and sweeping out the area. And this has height f of x and infinitesimal width dx. And by the way, this dx, when we take the limits, so the same way that when we did the limit taking an ordinary derivative, the limit as delta x goes to 0 of delta y over delta x, this limited out to dy by dx, the Leibniz notation for a derivative. Well, when I take the limit of these Riemann sums, which have a delta x in there, that those delta x's limit out and become this dx. And so again, I'm thinking of this very hand-wavily and informally as this red thing starting at A, and it has this infinitesimal width, and as we go, it kind of varies. The height changes. As f changes, the height of this stick changes, and we take this infinite sum of these infinitely thin sticks of changing height, and that infinite sum adds up to this thing here. And that's how you can think about this notation, is that this elongated s here is telling us that we sum from A to B, and what do we sum from A to B? Well, at each particular point, we're taking the sum over all of the x's, the infinitely many x's in between A and B, and as those x's vary, we take the height of the function at the particular point, we multiply it by this infinitesimal width dx, and then we add them all up. And that's, again, this line, kind of this infinitesimally thin line, starting here and sweeping out the area. And again, this is absolutely not what is happening. What's happening is that we're taking a limit of Riemann sums, and that's how we get this thing. We already saw that. But this is a very useful way to think about it. This is an intuitive way to think about it, which will help you understand sort of what's going on, both with the fundamental theorem of calculus, without having to do a formal proof, and also for part one, at least. And it's also going to help us to think about volumes of rotation in a much sort of clearer way. And we'll see that with this in hand, we can really sort of simplify the way we think about those, and make something which seems tricky actually not so bad. It's actually really not that bad, volumes of revolution, when you think about them in this way. But more on that in the next video.